Welcome back, guys. Today we have a problem in which you're going to be simplifying complex circuits into equivalent circuits and then using that to find currents and voltages. Let's take a look at the problem statement. In the circuit shown, an ideal battery is connected to a network of resistors. What is the potential difference across the 5 ohm resistor, and what is the current through the 6 ohm resistor? In this problem, we're asked to find the voltage through the 5 ohm resistor, and we're also asked to find the current traveling through the 6 ohm resistor. One approach to this problem will be to use Kirchhoff's laws many times for all these various loops in here, and then combine the equations and find the missing currents and the missing voltages. In this problem, that's overkill, and the reason is because we only have a single battery and we have a bunch of resistors. So these resistors can be combined just using the properties of resistors in parallel and series, and then from there you can combine this into a much simpler equivalent circuit. From there you can find the current traveling through the main branch. And then using Ohm's law various times, you can find other quantities in the secondary branches, the currents and voltages across them. So that'll be the approach here. To do this, we're going to have to draw equivalent circuits, so we have to combine these resistors kind of group by group, and I'll start that off right now. So let's take these two resistors first. They're in parallel because each end of the resistors connects to the same node on either side. So this resistor connects to this node on this side, and then they both connect to this node on the left-hand side. So they're in parallel. So let's use a formula for resistors in parallel to find out what the equivalent resistance through this entire loop would be. And that resistance is, so it's it's the reciprocal of each resistor added up is going to be the reciprocal of the resistance, the equivalent resistance, which is 4 ohms when you solve for that. So that tells us we can redraw this circuit with a single 4 ohm resistor in place of these two resistors, 6 and 12. So let's go ahead and do that. So now we have, on the top branch, we have 2 4 ohm resistors. And on the middle branch, we still have the same 3 and 5 ohm resistors. So I'll just write 4, 4, 3, and 5. And then the battery is still there, of course. All right, so this is the process we're going to use. And so what I'll have you guys do on your own is to do the exact same thing a couple more times. Combine these either in series or in parallel. And the ultimate goal will be to find a single loop with just one battery and one resistor. Take a minute and do that now. And pause the video if you need to. We'll come back and take a look. Starting from here, we can draw a couple more equivalent circuits. So in the top branch here, we have 2 resistors that are connected in series because they're connected end to end. And so if we combine those, when they're in series, it's very simple. Just add up the resistances. So 4 plus 4 is 8. So for the top branch, we can write that as a single resistor of equivalent resistance 8 ohms. And then same thing for the middle branch. They're also in series, and they add up to 8 ohms. So we have a circuit that looks like this now. The battery is in the same position with this equivalent resistance of 8, this equivalent resistance of 8, and then a 12 ohm battery. And now we can do it one more time. Here we have them in parallel because, again, each end is connected to the same node. And so these guys are in parallel, and that means that if you add up the reciprocals, you should get the reciprocal of the equivalent circuit. And a quick trick is that when you have 2 resistors in parallel that are the equal resistance, then the equivalent resistance will just be the half of those. So the equivalent resistance in this case will be 4 ohms. Okay, so this equivalent resistance, by combining these 2 resistors, will give us a single circuit, a single loop with only a single resistance of 4 ohms and then 12 volt battery. All right, and so now we basically reduce this entire circuit of a network of resistors to a single resistor. And the purpose of this is now we can find the current through this main branch here. So this branch has not been changed at all. So whatever we find for the current through here will be the current through this main branch in the first circuit. And that's very simple, just applying Ohm's law, which is 12 equals IR. So I equals 3 amps. All right, so that's the current through the primary branch. Now how can this be useful? Go back to what we're looking for. We're looking for the voltage across the 5 ohm resistor. So we need to find the current through that resistor because we know its resistance. We have the current coming through this primary branch, and we know that it's going to split right here. So the best way to do this, I think, is to kind of start at the very last diagram and work backwards one by one to find out the current through the secondary branches. In this case, we have a current going through here of 3 amps. It's the same thing in this diagram. It's coming through here at 3 amps. And then at this point, it's going to split into these two guys. And you can tell by symmetry it's going to split evenly. But to do it a little more systematically, we can kind of use what we know about the voltages across those branches one by one. Now, we have a current of 3 amps coming in through here. And we know that this node is 12 volts, this node is 0 volts. And that's the same across any point here. So this is also 12 volts, this is also 0 volts. So the voltage across this resistor is 12 volts. Same thing across this one. Whenever you have resistors in parallel, the voltage across each is the same. And so in this case, you have 12 volts across each of these resistors. So what I can do is apply Ohm's law across each of the resistors. So let me do that here. So that means that across this resistor I have 12 volts. And I'm looking for its current through that branch. And I know its resistance is 8 ohms. So as expected, I get a current of 1.5. And then the same thing for this one. So this will split evenly into 1.5 amps through here and 1.5 amps through there. Okay, now we can go back one more diagram. And we know that this guy is coming in through here of 3 amps. It splits into 1.5, and it splits into 1.5 in this direction. Now, we need to find the voltage across the 5 ohm resistor. We know the current coming through this branch is 1.5. And because this single branch does not split, the current traveling through any point of it will be the same. 1.5, 1.5, 1.5. So in particular, through that single resistor, the current will be 1.5 amps across a resistance of 5 ohms, which gives us a voltage of, so right, this is voltage of 5 ohms, is the resistance times the current, which is 1.5 times 5, and that gives us 7.5 volts. And that's the answer to the first part of the problem. Now the second part of the problem asks us to find the current through the 6 ohm resistor. And so you kind of want to do the exact same technique and go backwards from here to find out the currents through here, and then you can find the currents and or the voltages to find the current through the 6 ohm resistor. Take a minute and do that on your own, and we'll come back and take a look. We're asked to find the current through the 6 ohm resistor. So that's only in this diagram. After that, it's already been combined. The problem is that in this diagram, we can't use the fact that there's 12 volts across this, because there's not 12 volts across this branch. This branch is a sub-branch of a larger one. So maybe it'll be helpful if we could find out the voltage of the 4 ohm resistor, and then using that, we know that the whole thing is 12, so we can take away that voltage and then find the remainder across that. Once we know that voltage, we can divide that by the resistance to get the current through there. So let's take a look and find out what the voltage is across the 4 ohm resistor. Now the 4 ohm resistor, we know the current going through it is 1.5 volts, and we know its resistance is 4 ohms. So we can simply multiply those to get the voltage across it. So the voltage across the 4 ohm resistor is just the current times the resistance, which is 6 volts. So what this is telling us is that this entire branch from here to here, so basically from this point to this point, is a total of 12 volts because it connects directly to the battery here. And it's in parallel with the battery. We know that 6 volts is dropped across here, so another 6 volts must drop across there. So that tells us that the voltage across the 6 ohm resistor is a total of 12 minus the 6 that's dropped across the 4 ohm resistor. So it tells us the voltage across this is 6 ohms. And now it's trivial because we know if the voltage across it is 6 volts, and we know that its resistance is 6 ohms, we can easily find the current. Using Ohm's law, we get that this equals 6, and the resistance equals 6, so we get that the current is 1 amp. And this makes sense because, remember, we have basically 1.5 amps coming through here from this main branch that's split. And then it's going to split again when it gets to this node here. How does it split? The current's always going to want to travel the most in the direction, in the path of least resistance. And so if it has a choice to go here or here, basically it's going to have more current going through here because there's less resistance. And that's 1 amp going through, as we just found. And then through here, the remainder will go through there, which is 0.5 amps. So most of the current will travel through the path of least resistance, and the remainder will travel through that guy. And that's it for this problem. So let's take a look at the summary. We first drew a series of equivalent circuits to find the resistance of the entire circuit, which allowed us to determine the total current through the main branch. Then we determined the current through the secondary branches by working backwards from the final diagram, applying Ohm's law many times. We used the fact that the circuit elements that are in parallel have the same voltage drop across them, while circuit elements that are in series have the same current flowing through them. And so that's it for this problem. Like any circuit problem, this can be a little overwhelming at first, but if you approach it systematically step by step and then work backwards from the last diagram, you should be okay. If you have any questions or comments, please leave them on the link attached to the video, and we'll see you guys next time.